others on your own sometime to come if you are required to. Yeah, so you shouldn't get worried that we shall ask those things which are not here. But I was just mentioning that you can't exhaust sometimes all the material, but you just pick. Now, in your book, the reference book which you bought, we didn't have discrete uniform distribution. We just added it because it's also common and it is interesting, and maybe you shall have to compare it with the uniform distribution for continuous. So that's why it's good to start with it. So this one is not, it's just a simple one that if you have, say, x1 up to xk possible outcomes from an experiment, each of these is occurring with equal probability, then the random variable or the distribution which is arising from it will take on what we call a discrete uniform distribution. So the idea is that for a discrete uniform distribution, each of these outcomes occurs with equal probability. So if I had it 2, then each will occur with a probability a half. If there are 3, then each occurs with probability 1 out of 3. So the point to take home here is that each of the outcome in a discrete uniform or is equally likely. So if someone says equally likely, then you have to know that they are equal probabilities. An example which I can give you is like when my team A is playing against team B, and if I don't factor in any other things and the things are likely to occur naturally, I will say that maybe my team can lose, can win, or can draw. And if these events are going to occur naturally, or I can say if I don't factor in any other things, then I know that my team can win with the probability a half, can draw with probability, rather can win with probability a third, draw with the probability a third, as well as lose with the probability a third. So each of the possible outcomes occurs with probability a third. But sometimes not all events could occur with equal probabilities. Yeah, even in that football match, they could. If maybe your team A is playing B, especially these gamblers, there is a way they can bring in other things, the history against team A and B, blah blah blah, and then they try to give you odds ratios and so on. But the point to take home is that for the discrete uniform distribution, each of the elements is equally likely to occur. If there are 4, each occurs with probability a quarter. If there are maybe 10, each occurs with probability 1 out of 10. And in this example, we had 25 students and we wanted to pick some at random. And if each has an equal probability of being picked, then this can be looked at as a discrete uniform distribution. It's also for a fair die, each of these outcomes, 1 up to 6 can occur with probability 1 out of 6. So that's what we can say on the uniform discrete uniform distribution. Now for the Bernoulli, this one you must have seen it. All the groups, I'm sure the course lecturers must have introduced this because this is what comes first in the book. A Bernoulli trial has just 2 outcomes. One is called a success, another one can be baptized as a failure. So probability of having a success is P, and that of having a failure is 1 minus P, or we can denote it with Q. Yeah. In some of the notation we use Q. And then by convenience we can say let X take on 1 if it's a success, and then X takes on 0 if it's a failure. And we can write the mass function like that. And also the mass function can also be written in the compacted form like this. And this is the mass function for the Bernoulli. But again, you must be careful that when you are stating a mass function of a distribution, you must also give us the range. Yeah. So when you state it minus the range, then that is incomplete. So you have to state the range. Then you can also get the expectation, which is x times the f of x, 1 times probability of x equals 1, and then 0 times probability of x equals 0. Because in here, there are just two possible outcomes, and then with their corresponding probabilities, you should be able to get the mean as p, and then you can also work out the variance, but you have to first compute expectation of x squared, and then you use the formula to get the variance, which is p2. Again, here in the last remarks, we are saying that this Bernoulli can be done infinitely many times if they are independent. Trials, they can be done infinitely many times. But now what we want to derive from this, that sometimes you can do it if a Bernoulli is done n times and these are independent, then we are moving away from the Bernoulli to what we call a binomial. So that was the idea. And now this takes us to the binomial distribution. A binomial distribution can just be looked at as if it is arising from n independent Bernoulli trials. And now this binomial has two parameters, number of trials, which is n, and then the probability of success. So if someone tells you that a random variable is binomially distributed and it gives you the number of trials, n, and then p, then you should be able to do what you want with that problem, because once you have the parameters. Then again, how the mass function is stated. So this is how we state the mass function for binomial distribution. The binomial random variable, its distribution or mass function is given like this. And now also don't forget to tell us the range of values, yeah? And also this is also defined as n factorial divided by x factorial, then n minus times n minus x factorial, or n combination x. So that's the binomial, the mass function. And also you have also to remember this from high school, from the binomial theorem, that now, in fact, what we are showing here is that the binomial is indeed a probability mass function. So that's what we are showing here. Can we sum from x equals 0 up to n, and then we get 0? So we know the mass function is this, but now from binomial theorem, this is the same as that, p plus 2 raised to n. If you expand this is just a compacted one, but this gives you that. But now since p plus 2 is 1, then 1 raised to power n is 1. So it is indeed a probability mass function. Some examples. If you toss a coin 5 times and this coin is fair, of course, if someone just tells that a coin is tossed 5 times, then we assume that the coin is fair, and the head, probability of getting a head is a half, and that of getting a tail is a half. And then here in this case, it means that our n is 5, and then p is a half. Then you can do what you want. Then the question requires us to find probability that exactly 3 heads will appear, and that's why x is here. You substitute x equals 3, and then you should be able to get that. Another thing before we go away from the binomial is that you should note that for a binomial, we can even use tables. In some applications, you may need to compute a lot of individual probabilities for a binomial, but once you have the tables, it may be easier for you to get these binomial probabilities using tables, yeah? So that's why I want to illustrate an example using tables. Somewhere, somehow, you may need to use tables, but normally we don't dictate that use tables or a calculator, yeah? But it's good to know how to use both, so that in a particular application you may be at ease. Now, This example, the probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted the disease, what is the probability that Roman 1, exactly 5 survive, at least 10 survive the disease, from 3 to 8 survive the disease? Okay, for the first one, of course, this could be modeled as a binomial distribution problem, and probability of our success now becomes 0.4. Then n, because we're picking from n, from 15 people, then n becomes 15. And then we can get this probability that exactly 5, x equals 5, as like this. This is okay. Now, the problem arises when you want to get at least 5 survive. Yeah. Now, those are many computations to be done. Then you have at least 10, it means 10, 11, 12, all the way up to 15. But you can look at this probability of x greater or equal to 10, the same as 1 minus probability of x less than 10. I think this should be okay to all of us. As if looking at this, I can look at the complement of this. Of course, what should be in your mind is the sample space, yeah? There are 15 something. So that's why this is the same as that. But now this ranges from x less than 10, ranges from 0 up to 9. That's why I said here this is the same as 1 minus probability of x equals 0, x equals 1, all the way up to x equals 9. So I want to illustrate this, how to compute this using the tables. We can go to the table. I attached a table here. It's a binomial table. Now these tables are cumulative, yeah? They are cumulative. They are giving us probability from x equals 0 up to r. And you must be careful that these tables cannot be exhausted. There are very many tables because the value of p can be any value between 0 and 1. So no one can claim that he has tabulated the binomial tables and exhausted them. They are infinitely many because of this p. Yeah? But now you have to pick a table which gives you what you want. That's why you have to be careful. You have to ask yourself, because this binomial has two parameters. It has p and then n. So you see, is it the right p now? Yeah, it's 0.4. Is it the right n? Then I'm in the safe place. Now, if you look at these probabilities, they are cumulative, yeah? Probability of r equals 0. Now, these are the same as x's. R equals 0 will be that. But now this is for r equals 0 plus r equals 1. And for instance, this one is for r equals 0 plus r equals 1 all the way up to r equals 5. Now that's why they are cumulative. And as you can see, they are stopping at 1. Of course, it means that now these values below 1, they are zeros, yeah? If you can compute using calculator, and you have two parameters for binomial, p as 0.4 and n as 15, and your x is 14 or 15, you will see that you will get zeros here. Now that's why they stop here at 1. So sorry, that's why they stop here. So now this is how you can interpret these cumulative ones. And if I just need that of r equals 5, it can't be this, but I can say the cumulative up to 5 minus the cumulative up to 4, like that. So if we can go back to our problem, this one of at least 10, it means that if you can see here, I say this is the same as 1 minus the cumulative from x equals 0 up to 9. So I can get this value from the table. So kindly confirm that this value is that, and then Then for this one between 3 and 8, I can accumulate up to 8, and then I can take away up to 2 because I need 3 to be part. Yeah, that's why I have to stop at 2. This value can be gotten from the table, and also this value can be gotten from the table, and then the difference should be that. So you should note that sometimes you can get these tables when they are not cumulative, so you have to be careful. But the good thing with tables, they are always clear. They tell you what they are tabulating, as I will emphasize in the maybe how to use normal tables in the continuous case. So go through those examples. Where you get problems, please see someone to help you. Then you can also get expectation of a binomial in using 2 ways. One could be to look at a binomial as a sum of n independent binary trials. They should be independent, and they are going to be n, and each has the same probability, or the probability of success is p all the way. So if you look at a binomial as a sum of n independent binary trials, then and if they are independent, this is allowed. Expectation of the sum is the same as getting individual expectations, and then you sum them. And we know expectation of a binary is p, and now these are n, that's why you get np. Another way could be to use the definition of expectation, which is n, you sum all the possibilities but of x times the mass function, and then you manipulate here. You know the binomial moves from 0 up to n, and then from here to here it's not confusing because now this is the mass function. Now here, this is where the manipulation starts. Now because this is x, and when I sum x at 0, it will be 0, and now these are probabilities, they are positives. So it is as good as moving from x equals 1. But again, this x and x factorial, they can cancel, they can simplify them, because down here I can have x times x minus 1 factorial, and that's why here I have only this expression. So now from here, because I have x minus 1 here, I struggle to have also x minus 1 here by letting p go out, and also somewhere I'll need n minus 1 somehow, and then I manipulate. And at the end of the day, I have to convince myself that now this one, in fact, this one is the same as p plus 2 power n minus 1. We saw p plus 2 power n, yeah? I think here we had n and x, but now this is n minus 1, x minus 1. So, and luckily enough, since p plus 2 is 1, then 1 raised to power n minus 1 is 1, and that's why you have n times p. The variance can as well be done in 2 ways. You look at it as a sum of n independent binary trials, the same thing. You get the variance of each of these individual binary trials, and then you sum, since they are n, then that's why I have np2. You can look at the standard deviation, which is the positive square root, and so on and so forth. Yeah, it is challenging to use the definition of variance to get the variance of a binomial, but it can be done with ease. So the definition of variance is here, but now we need this expectation of x squared, but it's not easy to get. That's why I have to do it via this. You get this expression. Also, it's somehow involving, but you can do it patiently. And the same ideas, those values, you can start from the values which are giving us, which are not 0, because when x is 0, this term will be 0. When x is 1, this term will be 0 because of this. So you can move from x equals 2 up to n, and then I can also simplify this with this, and I say this is the same as x times x minus 1 times x minus 2 factorial, and then That's why this can cancel, and they can, because I have also x minus 2, you think over how we can have x minus 2 here, and also you can also try to think of it that you can have n minus 2 somehow, and then you pull out what is important, and you also reason that this is the same as p plus 2 raised to power n minus 2. Yeah. Now, having gotten that expression, that means that I have to know how, if I expand this out, what am I likely to get? When you expand this out, you get expectation of x squared minus x, expectation of x. But we needed expectation of x squared. So that's why you have to add you have to say now, to get expectation of x squared, then this has to cross as if you add, yeah, expectation of x. You have gotten this already. This is the mean, and then you also succeeded in getting this, so you should be able to get expectation of x squared. Once you have it, then you can use the definition and get the variance. So, and I'm hopeful most of you must have done it either in class or as an assignment, wherever, and then try to finish these examples of a binomial. They are not confusing, please. And I think I've said it all for the binomial. And in the next video, I'm just going to talk about Poisson and the other three common discrete distributions. And that should be good enough for you to go through this topic 5. And then we shall be telling you on what to do next. Yeah, thank you so much. I can stop sharing.